Friends, in this lecture, I would like to explain another topic based on the footings. See here, a reinforced concrete column of size 300 by 300 mm carries a load of 750 kilonewton. The safe bearing capacity of soil is 200 kilonewton per meter square and isolated column footing. So design an isolated column footing with uniform thickness. Use M20 grade concrete and Fe415 steel. So write down the given data. So they are asking to design a isolated column footing. So what is isolated footings? Footings which are provided under each column independently. So if we talk about combined footings means combined footing supports two or more columns. So but we are going to design here isolated column footing. So the given data, the size of the column given as 300 by 300 mm, both are in mm, carries a load which is P will be equal to 750 kilonewton and SBC of soil will be equal to 200 kilonewton per meter square. Design an isolated footing and given material will be 20 newton per mm square FCK and Fi will be equal to 415 steel. So here what happened means they given the size of the column like this. So both sides it will be 3 by 3. So here it will be 300. Here it will be 300. For that we have to design the footing. Okay, we have to design this footing. Okay, so this is the top view. So if I will talk about the side view, it will be like this. So this is the column, this is the size of the footing, but still we don't know what is the size of the footing, but the given data is only for the column and the column will base the axial load of around 750 kilonewton will be given. So for that we have to find the size of the footing. See here, first size of the footing, take down size of the footing. So for finding size of the footing, first take self weight of the footing. So load of the column will be given, P will be equal to 750 kilonewton. Then the self weight of this footing. So for finding self weight, we have to take 10% of the column load. So self weight of footing will be equal to whatever the load will be given here, column load, that will be taken as 10% of column load. So 10% of column load means 750 by 100, which is 75 kilonewton. So what is the overall load? This size of the column load plus self weight of the footing will be equal to total load. That one will be equal to 750 plus 75, which is 825 kilonewton. Then find the area of the footing. Area of footing. So area of footing will be equal to total load by SBC of soil. So that one will be equal to 825 by SBC of soil in the data will be given 200 kilonewton per meter square. So that one will be equal to 4.125 meters square. So generally the SBC will be like this. It is in terms of upward pressure like this. So it is denoted with some QU, Q like that. Okay, then after finding the area of the footing, so just to take down, this is in terms of square, so divide this footing in terms of length and width wise. For that I will take this one will be equal to 4.125 in terms of square root. So area of the footing will be equal to L into B. That one will be equal to 4.125. So both sides we are keeping same dimensions. Okay, so it will be around B will be equal to 2.03. So therefore it will be equal to approximately 2.1. So we have to adopt this one. So first find the area of the footing, and then here it is not mentioned that which type of footing you have to design. So for example, if they will ask about here, you have to go for square footing, then you can choose the dimensions like this. So B square will be equal to this much, area of the footing will be equal to, both sides it will be same like B into B. So like how I am taking here. So if it will be rectangular footing they are asking, means you can take L into B like this. So generally area will be length into breadth, it will be 4.125. So here the column will be in square. In the question they will mention 300 by 300. So it is always convenient to prefer square footing if it is not mentioned in the question. But if it is mentioned in the question, you can go for rectangular footing, means at that time you can change the dimensions to suitable this area. For example, length will be some around 1.9 or 1.8 or 2.2. Maybe it will be different, which the length and breadth will be different, you will get in terms of rectangle. Entire procedure remains same, but here we have to change the dimensions according to the square or rectangle. Here in the question they didn't mention anything, therefore for square column I am preferring square footing only. So therefore I am taking B into B, and then the adapter size will be 2100 mm, both on lengthwise and breadthwise. So here we will confirm that our size of the footing will be equal to 2100 2100. Okay, suppose if they will asking about circular footing at that time, so area of the circular footing will be equal to pi d square by 4. So here you have to find out this dia based on this footing. See here, then you can find the dia, and like that you have to design for the circular footing also. So if it will be rectangular, choose length into breadth wise. If it will be square, take down B equal to this value, and if it will be circular, take down pi d square by 4 equal to that value. So here you will get the diameter. Then goes to the upward soil pressure. See here, next step is upward soil pressure. So what is the formula for upward soil pressure? So soil pressure at ultimate load. So we have to find, the formula will be soil pressure at ultimate load. QU will be equal to PU by area of footing. Area of footing. So here we have to take in terms of factored load. So if you want factor load, the given load will be 750, and factored means add 1.5 times extra. Then what about area of the footing? So already we adopted, size of the footing will be equal to 2.1 by 2.1. Take down that one, length into breadth wise, which is 2.1 by 2.1. So if you simplify, you will get around 255 kilonewton per meter. So the value in terms of Newton per mm square will be equal to 0.255 Newton per mm square. So this is the upward soil pressure at the ultimate load. Then next step is to find the depth of footing from bending moment considerations. Depth of footing from bending moment considerations. So what is the formula for finding depth generally we are choosing each and every time mu will be equal to 0.138 fck b into d square. Here we have to find the depth based required depth based on the this formula. For knowing this one, we want mu value here. So here for finding mu, what is the procedure? See here. So this is the footing. The size of the footing will be around 2100 mm in lengthwise and breadthwise, which is square footing. And the size of the column will be 300 by 300 mm. 300 by 300 mm. So for finding the depth, so always the critical section is at from the face of the column. So the face of the column will be this one from here. Here also this is the face of the column. 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 So there will be four sides equal because of the square column and square footing. So for finding bending moment, the critical section for bending moment will be at the face of the column, means from here. So I will choose this face, exactly any one face of the column. If you want, you can choose right side also, but I will choose any one face here. So how much this distance will be? For example, if you see the total distance here, it will be 2100 from here to here. So I am removing this exactly this part 300 and again this part also. So this part will be equal, this part will be equal, in between it will be 300. So therefore what I am doing means 2100 minus 300 means I am removing this part, means I am taking this total footing. Okay, so it will be around 1800 and again I am exactly dividing this half for getting only one face of the column, which is 900. So the value from here to here, the total length from this to the face of the column will be equal to 900. So this value will be 900. So I am just in half, means from here to here it will be 900 and this remaining part will be 300. Like that I am dividing. So this is the critical section. So for finding, so see here, so this is the shaded area. This shaded area is the critical section for bending moment, which is at the face of the column. So we know that this will be just like cantilever. So here it will be fixed and remaining part will be free. So here what is the soil pressure acting here means it will be 0.255. The soil pressure acting at this section will be QU, that is 0.255, and up to what length it will be in the total span of 2100. So this is the load which is acting on this end in the shaded area. So at what length? So it will be around 900. So what is the formula for finding bending moment? For example, for simply supported load, for simply supported beam, if an UDL is acting, the value will be WL square by 8. But for cantilever position, if an UDL is acting, the load will be WL square by 12. What is W here? Soil pressure into its total breadth. Here L will be 900 divided square by 2. So simplify this one. You will get bending moment will be around 216.88 into 10 to the power of 6 Newton mm. So what about shear force? We know the condition for shear force also, which is W into L for cantilever. Okay. Here we have to find this depth. For finding the depth, substitute this moment formula here, moment value here, 216.88 into 10 to the power of 6 and remaining value will be equal to 0.138. FCK will be equal to 20. B value. What is the B value here? So here in the formula, in place of this B, you can take down capital B, which is a total B value. That is from here to here. So here in the lengthwise we are taking 900, the breadthwise taking 2100. So take down this one as the B value, that is 2100 into D square. So find out this D value. substitute in your calculators, you will get a D value will be approximately 193.4 mm. So again take down this as approximation around 200 mm. So here this is the depth required for the footing. So for example, we are seeing from this top view. So how much depth we have to provide here? For that only we are checking this one. So the depth required for footing. So see here. Here we are calculating this depth. First effective depth based on that overall depth. Okay. So the depth required for footing will be, here obtained value will be 200. So one more thing you have to remember here is, to resist shear in footings, whatever the depth obtained for bending here, it will be taken as twice. For example, you will get depth will be around 200 mm means we can take down the value will be twice, because depth required to resist shear in footings is much higher than required for bending. So you have to assume the depth will be twice for bending moment consideration. So each and every time, whatever, even you can calculate some rectangular footings or square footings at the time also, if the depth will be some 250 means automatically you can take down twice whatever the depth adopted here, obtained here. So your adopted depth will be equal to 400 mm, which is effective depth here. Again for overall depth, choose 50 mm effective cover extra and adopt 450 mm higher value. So therefore your overall depth will be equal to 450 mm and effective depth will be equal to 400 mm. Then provide the reinforcement for this one. So next step is reinforcement details. So generally for the reinforcement we are using only one formula, which was here page number 96. See here, this is the formula. Each and every time we are using this formula only, but just to take down in place of small b, capital B. Okay, so I will make use of this formula here. Mu will be equal to 0.07 Fi AST D into 1 minus Fi AST by FCK capital B into D. Okay, then so substitute all the values whatever obtained here, 0.87 into 450 into area of the steel. So depth taken here is 400 and again 1 minus 415 into area of the steel. FCK will be 20, 2100 into effective depth will be equal to 400. So simplify, you will get area of the steel. So just a general procedure only, all these things are. You will get area of the steel will be 1562 mm square. So like slabs, we have to provide spacing here also. So spacing will be equal to AST into B by AST. So check the formula. The spacing formula here for using footings will be small AST into B by capital AST. And here we know the minimum number of dia bar using for footings will be 12. So I will check with the same dia only. Pi 12 square by 4 into B value will be 2100 divided by this capital AST. So the AST will be 1562, which is obtained here. If you simplify, your spacing value will be 152 mm. So approximately it will be equal to 150 mm. So adopt the spacing lesser the value, some round of value. So here provide 12 dia bars, provide 12 dia bars at 150 mm spacing center to center. So this is the main reinforcement. Then so we have to provide the spacing in both the directions. So after finding the reinforcement, then check for one-way shear. So for footing, we have to check both one-way shear and two-way shear also. So this is also same. So this is the footing and this is the column. So we taken the critical section for finding the depth will be at the face of the column, which is at a distance 900 mm from here to here. In the overall length is 2100 mm. So here also it will be 2100 mm. So we know all these values. So the column will be around 300 by 300 only. But each and every time we have to remember one thing. For finding critical section for one, so for finding check for one way shear, the critical section for one way shear is always at a distance of D from the face of the column. So what is D here? The D value will be equal to 400 mm what we adopted. So in this 900 again we have to remove this 400. So the remaining value will be 900 minus 400 will be 500. Means the critical section is at a distance of 500 from the face of the column. Again I will mark with the shaded area here. So always remember this one. The critical section is at a distance of D for one way shear. So I will mark with the shaded area. So how much its length? Its length will be around 500. Then, so if your tau c value will be greater than tau v, so one way shear is also in safe side. So first check the tau v value. So what is the formula for tau v? So we know this formula from starting itself. Tau v will be equal to Vu by capital B into D. Generally it will be small b into D. So here capital B will be 2100. Then what about Vu? Vu will be the shear which is Wu into L. So what is Wu here? Already we know W into U will be equal to 0.255 into its overall length, breadth, 2100. And L is here the critical section which is acting 100. So I am telling like this. So this is QU into 2100 and this distance is 500. That is WL is equal to 500 by, sorry, this is the value ends up to here, W into L. So the value will be 267750 in newtons. So after obtaining this Vu, check with the formula. That one will be equal to 267750 by capital B value will be 2100 into small d value will be 400. So it will be 0.318 Newton per mm square. So your tau v value will be equal to 0.318 Newton per meter square mm square. Then for finding this tau c, we know the condition. First we have to find percentage. So where it will be? It will be in the page number 72. So we know the design strength of concrete. So which was in page number 73. Design strength of concrete tau c value. PT will be equal to 100 AST by B into D. So here in place of B, you can take spacing S into D. Okay. So the just small modifications in the formula. You please remember that one. 100 AST by S into D. So D is small d here. So 100 area of the steel we are taking pi into 12 square by 4. We are adopting this much dia. Spacing will be around 150. Effective depth will be 400. So you will get around 0.2%. See here in the table, check once where your 0.2 lies. So your 0 point lies here is between 0.15 and 0.25. So exactly middle value 0.20 value. See here 0.15 and 0.25. Want the middle value, that is 0.2. So for M20 grade concrete, so one will be 0.28 and 0.36. How many digits here? The difference is 0.8. So I will take exactly 4 digits different for exactly half of the distance, means 0.4 is the half distance. So I will take 0.32 is the correct middle value for 0.2. Why? Because we want exactly half of the value. So if you want 0.23, 0.21 or 0.1617 means we will go for interpolation. There will be no other procedure for finding this one. So already I explained so many videos how to calculate the interpolation, but here the very easy. 0.2 is the exactly middle term between these two. I will choose directly that 0.32 is our permeable shear stress. So tau c will be equal to 0.3t in Newton per mm square. If you observe, so this tau c will be 0.32, which is greater than tau v. That will be equal to 0.318 Newton per mm square. So here, if tau c will be greater than tau v, your shear will be safe. One way shear will be safe. Okay, which is safe inside. Then similarly, go for two-way shear. So for one-way shear, what we did, we will taking from one side at a distance of d from the face of the column. But for two-way shear, it will be small difference here. So this is the footing. So again you can take down all the dimensions. Again this is the column around 300 by 300 mm. But for finding two-way shear, the critical section is at a distance of d by 2 from all face of the column. So see here, d by 2 from the face of the column, like this, all faces, d by 2 from here. So here also d by 2. This side also d by 2. This side also d by 2. So each and every face it will be at a distance of d by 2. Okay. So here d value will be 400. D by 2 means 200. So here also 200. Here also 200. Here also 200. So I will check the values. It will be like this. So it will be like this. See here. So d by 2 from this face. Similarly d by 2 from this face. Similarly d by 2 from this face. Similarly d by 2 from this face. So this is the rough diagram. So see here, right round, I am drawing like this. So what is the remaining area here? So it will be 200 and the overall area will be. So take down this one will be d by 2 plus d by 2, which is d, and column will be b. So which is b plus d in right round side. So here also b plus d. So how much it will be? So this b plus d value will be 300 plus 200, which is 500. So here it will be 200, here it will be 200. So overall 700. 700. So this side also 700 it will be. Okay. Then, so entire this area is the critical section here. I will mark with the shaded lines like this. So always remember, check for two-way shear. So check for two-way shear. Check for two-way shear. So you remember one point here. So the critical section is at a distance of the critical section is at a distance of d by 2 from the face of the column. D by 2 from the face of the column. So I shown all the dimensions how it will affect. D by 2 means overall 700 area. So what is the remaining shaded area here? If you remove all this area like 700 into 4 times, you will get overall perimeter 700 plus 700 plus 700 plus 700, this side 700, this 700, that is perimeter. So perimeter of that critical section will be equal to 4 times of this 700, which is 2800. Okay, so we are seeing from top view. For example, if you see here, this is only top view, and what about its depth? We know the depth here, so it will be like this. So the depth is around d value taken from here to here, it will be 450, and the column will be here 300, and this perimeter of the section will be around sorry, the column dimension also, which is equal to the internal one. So take down approximately with that dimensions only, and again perimeter area value will be equal to perimeter value will be equal to, see here. So in the front view I am drawing like this. So here the overall depth will be how much the perimeter. So I am talking all for this footing only, not for the column area. So I am drawing only for this column area. Take down for footing area. So this is the column area. Critical section perimeter will be this one for the footing. So I am showing in the 2D view. So 4 times of 700, which is 2800, that is the perimeter. If I want area will be equal to this perimeter into its depth. So the overall depth, how much the footing will be, it will be equal to, so I am taking in terms of effective depth, which is 480. Why? Because we are providing reinforcement from the effective depth only. So therefore I am choosing this d value here. So how much it will be? It will be around 1120000. Then next step is for two-way shear. Finding VU2 value. So the formula will be QU into area of that shaded portion. So what is here area of the shaded portion? See here, this total area, that is in the overall 2100. Every side we are removing 700. So how much it will be? In the overall side means 2100 by 2100 minus 700 by 700. So you will get the area of this shaded portion. So for that QU value will be equal to 0.255 into area of the shaded portion will be equal to 2100. So this is the overall area. I am removing the shaded portion 700 by 700. Okay, then if you simplify, you will get VU2 value, that will be around 999.636 into 10 to the power of 3 in terms of Newton. Then two-way shear stress formula will be, so please remember the formulas in the footing. We know that stress will be equal to force by area. that is 996, that is VU2 here, 999.6 into 10 to the power of 3. So what about its area? So its area is around, so we find here area of the critical section will be equal to this one, 2800 by 400, that is 11,200,00. So if you simplify this one, you will get a 0.89 Newton per mm square. Then check with the permissible punching stress. So permissible punching stress. So all these formulas there in the code book also. So your tau p value will be equal to 0.25 square root of FCK. Just to check with the code book once. So all these formulas there in the code book also. So simplify this one, 0.25 square root of 20. It will be 1.12 Newton per mm square. So here if you observe this one, this tau p will be greater than tau v value, which is 0.89 Newton per mm square. So if your tau p will be greater than tau v in two-way shear, so your two-way shear is also safe here. And again in the one-way shear, what is the condition? Your tau c value will be greater than tau v, then your one-way shear will be safe. So you please remember this one, it will be acting at a distance of d from one face of the column, but here it will be acting at a distance of d by 2 from both faces of the columns. First find the perimeter of the section and then find the critical section area. Then check for bond length. Check for bond length. So already I told you how we have to check the bond length for the cantilever beam. So here also the footing is designed as a cantilever with reinforcement subjected to design strength of the column face. So while checking with the one-way shear, see here you very clearly. So it will be designed like as a cantilever. Therefore, we have to check the bond length also for the footings. So what is the formula? As per in IS 456, the page number will be around 42. I will show once the formula where it will be. See here, LD development length will be equal to dia sigma s by 4 times of tau BD. So we know the sigma is equal to 0.87 F5 dia by 4 times of tau BD. 4 times of tau BD. And again you can remember one more point here. For deformed bars conforming to IS 1786, these values shall be increased by 60%, and for M20 grade concrete, tau BD will be equal to 1.2 and it will be increased to 60%, means tau BD equal to 1.2 into 60% means 100 plus 6, 1.6. So totally how much we are taking here in the formula, 0.87, Fi will be equal to 450, diameter will be equal to, already we chosen the diameter around 12 bar, and 4 times of this 1.2, tau BD will be equal to this value, 1.2 into 1.6. If you simplify, you will get around 564 mm. Okay, so that is the bond stress calculation. So it will be around 564 mm here. So from the face of the column, for one-way shear, you see here, for taking bending moment calculations, so minimum depth required for bending moment considerations from the face of the column will be taken as 900 mm. But what is the development length required? It will be 540 only. It will be 540 only. So your face of the column will be higher than the development length, which is 900 greater than the development length. So it is also safe inside. Okay. Then move to the next step, which is bearing pressure. Okay. I will go with the next step, that is bearing pressure. Check for bearing pressure. So before going to the bearing pressure, first see here, the compressive stress in concrete at the base of the column is transferred by bearing to the top of the support footing. See here, I will show the image. See here. So this is the column and this is the footing. So you can check the bearing pressure here. This is the A1 of the column. So the total area will be taking like this. The column width plus up to slope 1:2, it will be distributed. The load from the column, it will be distributed to the footing from both sides, either left and right side. This is in 2D view. And again you can take this view in the width wise. So it will be like same only. So here also this view we can observe column like this only. So I am showing in 3D view. Okay. So A2 will be this part and A1 will be this part. So which is the overall area 2D plus B into plus 2D. So the compressive stress in concrete at the base of the column is transferred by bearing to the top of the supporting footing. The bearing pressure on the loaded area shall not exceed the permissible bearing stress. So here see here, actual bearing pressure, I will write down the statement here. Actual bearing pressure equal to ultimate load by area of column less than permissible value. So I seen all these statements in the code book. I will check with that code also, which was in page number 62. You see here, whatever the statement I told now, it will be in page number 62. See here, page number 65. The compressive stress in concrete at the base of a column or pedestal shall be considered as being transferred by bearing to the top of the supporting pedestal or footing. The bearing pressure on the loaded area shall not exceed the permissible bearing stress in direct compression multiplied by a value equal to greater than square root of A1 by A2 but not greater than 2. See here, A1 will be supporting area for bearing of footing, A2 will be the loaded area at the column base. What I shown exactly here, this is the A2 and this is one will be the A1. First check with that value. So the thing will be in code book which was in page number 65 in your IS 456 2000. So I will continue the problem here. So you people know the diagram. So what is your area width of the dispersion load? So that is this total area taking from here to here 2D plus B plus 2D. So here we know the column will be 300 in mm and this B value will be equal to 300 and 2D. So which is around D value will be taken 400. So that will be 800. Here also it will be 100. Overall 16, 17, 18, 1900. So 8 2 just 16, 17, 18, 19. So overall the length will be 1900. So taking from here to here it will be 1900. Then this 19 will be taken in lengthwise. Again there will be widthwise also. So that is 1900 into 2 is the A1. What about A2? A2 will be the loaded area of the column base. So 300 by 300. So 300 by 300 is your A2. Then, so how much you will get this one? So you can simplify like this. So I will take in terms of meter. A1 will be equal to 1.9 by 1.9, which is 1900 by 1900. So it will be 3.61 in meter square. A2 will be equal to 0.3 by 0.3. In terms of meter square, it will be 0.09 meter square. So we know the condition square root of A1 by A2. So how much you will get this one? So square root of 3.61 by 0.09. It will be 6.33. But what is given in the code? In our code they will clearly mention it does not greater than 2. At that case what we will do, whatever the value obtained here, it will be restricted to 2 only. So approximately we are taking this one value will be 2. Then what is the formula as per class IS 46 value? So it will be (0.45 FCK along with the permissible bearing stress. So the formula will be this one. That one will be equal to the permissible bearing stress. The permissible bearing stress will be equal to 0.45 FCK square root of A1 by A2. So this A1 by A2 will be restricted to 2 here. Okay. Then what about 0.45 into FCK? So you can check with that value, that is 0.45 into FCK will be 20 into this 2 value. So I will write down here clearly 0.45 into 20 into 2. So the value will be around 18 Newton per mm square. So this is the actually allowable bearing pressure, means permissible allowable bearing pressure, that is 18 Newton per mm square. Then check the actual bearing pressure. So what is the actual bearing pressure? So we know the general formula, pressure will be equal to load by area. What is ultimate load we are taking for the calculation? 25 into 10 to the power of 3. Area of the column will be 300 by 300. It will be around 12.5 Newton per mm square. So based on our design calculation, the footing allowable or permissible bearing pressure will be 18, but actually bearing pressure on the footing will be 12.5. So therefore allowable bearing pressure will be greater. So hence our design will also safe, because actual bearing pressure will be this much, but the allowance will be higher. Therefore it is safe only. So bearing pressure also safe. So like this you have to check the bearing pressure also. Then after that you can go for the detailings of the reinforcement. So that is very easy. See here. So from the top view, if you observe this one clearly, so the dimensions 2100 by 2100, which is the square footing. So both are B by B. So the reinforcement what we calculated, it will be provided on both the direction, that is 12 bars at a spacing of 150 mm center to center. And again if you observe this one, so what is this one? This one will be the column. If you observe from the top view, so here if you see here, this top you can observe what you will see. So this top you can see means you will observe only this column. So this column, okay, so the column will be this one, stirrups and the columns, dia bars. So you are observing this dia bars for providing stirrups, and this bendings which are provided the development length. So all these things will be observed here. The column cranked here, bending value. So the column will be bent here like this. The reinforcement of the columns bends like this. So we are observing that one. So these are the reinforcement provided, that is 12 bar at a spacing of 150 mm center to center. And here if you see from this view, the straight bars will be appearing round like this, and these bars will be the straight bar. Okay, so this is the detailing of the reinforcement. Comparing to other detailing, it will be very simple. So you please check once. Thank you so much for watching this video. If you really like this video, please like this video, share it to your friends and subscribe our channel. Thank you so much.